Okay, here we are asked to solve this differential equation, and the differentials are separated, so you would think that it's an exact differential equation, and it is. Okay, it's also linear, it's also separable, and it's also homogeneous. And we're asked to solve it. Now, you can see here that in this, at least on the left-hand side, the differentials have been separated. So if I was about to take a bet on this, I would bet that this was an exact differential equation. Okay, because it's of the following form. Where m is 2xy and n is x squared. Now, the question is this star equation exact? Well, we have to check one important thing. The partial derivatives of m and n have to satisfy certain conditions. So we calculate m sub y, or dm dy. So if I look up here, calculate the partial derivative with respect to y, I get 2x. And n sub x. Okay, so n sub x, differentiate that with respect to x, it's just 2x. Now we see that these two partials are equal and they're continuous. Okay, that's one thing that people leave out of the study of exact differential equations. You always check this, but strictly speaking, you should check whether these are actually continuous functions or not. Okay, they will be if they're polynomials. They usually are. So both are continuous. So yes, star is exact. Okay, so what does that mean? All right, well, this gives us the green light to assume a solution in the following. So it's like an implicit form, if you like. Remember, y is a function of x here, and c is just a constant. What we would like to do is determine big F, okay? The form of big F. Now, we may or may not be able to write y equals a function of x. Having this sort of implicit form is usually okay. All right? All right. Furthermore, we have the following. Well, just via the chain rule, if I differentiate both sides of this expression with respect to x and line it up with this one, we can make the following conditions hold. F sub x equals the m function, which is 2xy. And f sub y, again, partial derivatives here, is n, which is x squared. So in other words, we have two partial differential equations here. And the easiest way to solve them is via integration, right? Integrate the first one with respect to x, integrate the second one with respect to y. Okay, so integrate the first one with respect to x. So imagine y is fixed, integrate this with respect to x, so the 2x will go to an x squared. Now I don't get a constant of integration here. Can anyone suggest what I'd get? Because I've got a partial derivative up here. A function of, correct. So let's say g of y. So that's from the first one. So integrate the second one with respect to y. The left-hand side will become big F. And I'll get yx squared plus, not a constant, but a function of x. Okay, so now what we would like to do is just compare. Basically, we want one and the same expression here. Okay, so if you look here, I've got x squared y and x squared y down here. So what would these two functions of integration be? So you compare these two expressions, want to make them equal. Let's G and H are both going to be 0. So our expression up here, big F will be x squared y and set it equal to a constant. Now, so that's our implicit form. Okay, now it just turns out in this particular solution you can make y the subject. So if you want to, you can say y equals a constant over x squared. Okay, here we are asked to solve this differential equation, and the differentials are separated, so you would think that it's an exact differential equation, and it is. Okay, it's also linear, it's also separable, and it's also homogeneous. Okay, but I can think of an even quicker way of solving this problem. Okay, I'm going to connect the differentials again. Okay, now, what is this the derivative of? The left-hand side is the derivative of a product. What is it? Well, I've got a dy dx there. I've got a y there. I've got an x squared there and a 2x there. Correct. By the product rule. Okay, the derivative of that times that, which is there, times the derivative of x squared times y, which is there. So actually, you can do that in one line. So we integrate both sides, as you were saying, to get yx squared equals a constant. Okay, now you may look at that and go, oh, Chris, I would have never thought of that. That's okay. All right, it takes a trained eye to look for these things. But, you know, I solve a lot of these problems, and I want to always look carefully at the structure of the differential equation and see if I can use simple ideas from calculus. Here it's just the product rule to simplify things as much as possible. Okay? So think about it.